Hello students, welcome to AIMS India online classes. This is chemistry session. Here we are discussing about atomic structure chapter. In this session, we are going to see a practice sheet related to this chapter. In the earlier session, we have seen practice sheet 1, which contains completely single correct answer type questions. Now, in this practice sheet 2, we are going to see different kinds of questions like multi-correct answer type, statement type, assertion reason, and level 2 questions. Okay, first let us say about multi-correct answer type questions. Here, for each question, we may get one or more than one correct answers. So, read carefully the question and answers and select the correct options. Okay, first question, Bohr's theory is not applicable to. Yes, we know Bohr's theory is applicable only for the single electron species like hydrogen and hydrogen-like species which are containing single electron in them. For example, if you see hydrogen atom, it has single electron. If you see helium plus ion, He plus, it also will be containing one electron. Li plus 2, also containing single electron. Like this, the atoms or ions which are having the single electron, only for those this Bohr's theory is applicable. The atoms or ions which are having more than one electron, for those Bohr's theory is not applicable. Now see here, which are having either more or less than one electron, for them Bohr's theory is not applicable. We see first one, helium. How many electrons will be in the helium? There will be 2 electrons in helium atom. So it is not applicable here. What about Li plus 2 ion? We know lithium has 2 electrons. In Li plus 2, there will be only 1 electron. Lithium, 3 electrons will be there in lithium. So in Li plus 2, only 1 electron is present. So we can say as this single electron species. For this, Bohr's theory is applicable. Now if you see He plus 2 or helium 2 plus ion, helium contains 2 electrons and He2 plus contains 0 electrons. So for this also Bohr's theory is not applicable as it has no electrons. If we see H plus, we know hydrogen has 1 electron. He plus has hydrogen plus H plus has no electrons. It also having 0 electrons. So for this also Bohr's theory is not applicable. Now A, C, D. For this Bohr's theory is not applicable. Bohr's theory is applicable only for the species with 1 electron. Okay, for this it is not applicable. Next question. Heisenberg's uncertainty principle is not valid for. Actually, Heisenberg's uncertainty principle is applicable for the microparticles which are moving with high velocity. So the minute particles like electrons, the particles with very small size and moving with high velocity, only for those this Heisenberg's uncertainty principle is applicable. Like electrons. See here, moving electrons. Yes, for this principle is applicable. Motor car. For these kind of heavy particles, this principle is not applicable. And for the particles in the stationary position, which are not moving, for those also, this principle is not applicable. And even revolving planet, for these heavy particles like planets also, this principle is not applicable. Okay, for these also it is not applicable. Now for the stationary particles and for the revolving planets and even for the motion of the cars and vehicles, this principle is not applicable. Only for the particles with very small size and with a high velocity, only for those this principle is applicable. Heisenberg's principle is applicable only for microparticles which are moving with high velocity like electrons. So only for the electrons it is applicable, but here they're asking for which it is not applicable. So for these three. Next one. Which of the following elements are having more number of electrons with the spin value plus half than electrons with the spin value minus half. So they're asking which of these elements are having more electrons with the positive spin than the electron with negative spin or anti-clockwise spin. See, first, if you to know that, let us write the electronic configurations of these elements so that we can understand easily which are having more number of electrons with a positive spin. See, sodium, we know its atomic number is 11 and its configuration is like this: 1s2, 2s2, 2p6, 3s1. Now, if we observe the electrons with a positive spin or clockwise spin or with value plus half, totally there are here 1, 2, 3, 4, 5, 6, totally 6 electrons are there. And electrons with a negative spin or negative uh, anti-clockwise spin. How many are there? 1, 2, 3, 4, 5. Only 5 electrons are there. So sodium has electrons with positive spin more than the electrons with negative spin. So it is having more electrons with the half spin, positive half spin. If you see boron, atomic number of boron is 5 and its configuration is shown like this. Here I think you understand that electrons with shown with the upward direction arrow mark are having clockwise spin and their spin value is plus half, and electron shown with the downward arrow mark represents electrons in the anti-clockwise spin and their spin value is minus half. Now if we see in case of boron, electrons with positive spin, how many are there? 3 electrons. And the electrons with the negative spin, only 2. So this also have more electrons with the positive spin. Next about carbon. Its atomic number is 6 and its configuration is 1s2, 2s2, 2p2. Now, how many electrons with the positive spin? Only 4 electrons are there. With the anti-clockwise spin, only 2 electrons. So this also has more electrons with positive spin. Let us see helium. Atomic number is 2 and its configuration is 1s2 just. So electrons with the clockwise spin only 1 and electrons with anti-clockwise spin also only 1. So only both are same number. How many electrons with the positive spin? The same number of electrons with the negative spin also. So it won't come under. Only first 3 elements sodium, boron, carbon are having more electrons with the positive spin than the electrons with the negative spin. Okay, next one. Which of the following configurations violates Hund's rule? So they're asking which electrons or which configurations are violating Hund's rule here. So what is Hund's rule? Hund's rule states that electrons are the orbitals which are having same energy are called degenerate orbitals. So according to Hund's rule, all the degenerate orbitals will be filled with a single electron first. Then only pairing of these degenerate orbitals will take place. So the orbitals present in the subshell are called degenerate orbitals because they will be having same energy. Now if you observe first configuration given here, after completion of this there are electrons are occupying these 3 degenerate orbitals. So each orbital is occupied by single electron here. So this is correct according to Hund's rule. It followed Hund's rule, you can say. Second one, if you see here also, these 3 degenerate orbitals are occupying a single electron only. So followed here Hund's rule here also. Next, if you see the third one, here also all the degenerate orbitals are occupying a single electron. So this is also following Hund's rule. And if you observe the fourth one, here there are 3 degenerate orbitals. Instead of filling these 3 degenerate orbitals with the single electron first, by keeping this vacant, pairing taking place here. So this is incorrect according to Hund's rule. That means it is violating here Hund's rule. According to Hund's rule, first all the degenerate orbitals should occupy single electron. Then only pairing should be taken place. But here, without filling this degenerate orbital 1 with the single electron, pairing has taken place here. So this is violating Hund's rule. Okay, this is the answer. It is violating Hund's rule. Next one, which of the following orbitals have same n plus L value? So what is n plus L value? N representing principal quantum number value. L representing azimuthal quantum number value, which is taken from the subshell in which electron is located based upon the subshell. Now if you see the first one, 3D, n plus L value of 3D is 5 because n value is 3 here and L value for D subshell is 2. So total we get 5. What about 4p? N plus L value of 4p is 4 plus 1, 5. And for n plus L value of 5s, 5 plus 0, 5. And for 5p, it is 6. So which are having same n plus L value here? 3D, 4p, 5s. These three are having same n plus L value 5. So this will come under answer now, except 5p. Then next question, comprehension paragraph type questions. Let us see first the paragraph. The set of quantum numbers used to locate an electron in an atom are known as quantum numbers. There are 4 quantum numbers. They are principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. Now let us see questions based upon this. First one, which of the following sets of quantum numbers is not possible? See here, n value 2, that means second shell, it may be existing, and in that n value, L values may be from 0 to n minus 1. So here it may get L values 0 and 1. So it is given here 1. So it is also possible. And M values will be minus L2 plus L, including 0. So here M values may be minus 1, 0 and plus 1. So they have shown here 0. It is also possible. So this set of quantum numbers are possible values. And if you see here, n is equal to 2 means second shell, L value may be 0 because L values possible values are 0 and 1. So it is given here 0, it is possible value only. And M values, if L value is 0, M values will be, as we know, minus L2 plus L including 0. So here L value itself it is 0, so M values will be also only 0. But here they mentioned minus 1, which is not possible value because L value is 0. So M value also will be 0 because M values will be from minus L2 plus L including 0. Okay, it should be 0 but not minus 1. It is not possible. Okay, this is the correct answer. If for L is equal to 0, possible M value is only 0 but not minus 1. Okay, it is correct now. Next, which of the following sets of quantum numbers is correct for an electron in 4f orbital? So for the electron in the 4f orbital, if you read the quantum numbers, what will be the n value? N value should be 4 because it is in the fourth shell. So n value should be 4. So here n value given 3. So we can eliminate this option. It won't come under. And f value, L value given based upon the subshell F. If the subshell is F, then what will be L value? L value will be 3 for F subshell. So L value should be 3. We can eliminate this also here because they have shown here 4. Now out of these two we have to check. If L value is 3, then what will be the L value, M values? M may get, that means magnetic quantum number may get values from minus L2 plus L, where L is azimuthal quantum number value. Here L value is 3. Then M values will be from minus 3 to plus 3 including 0. So that is minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Among these 7 values, 1 may be there for M value. But here, if you see in this, M value they have shown plus 4, which is not possible, which is beyond the M values. M may get values from plus 3 to minus 3 only, including 0. But they shown here plus 4. So it is not possible. So it is possible. And S value may be either plus or minus half. plus of or minus of. They shown here plus of, this may exist. So the correct set of quantum numbers for the electron present in the 4f orbital is this. Remaining three are incorrect. Okay, next question. Matrix matching type question. Here they make two columns. We have to match the one in the column one with column two options. So here we may get one or more than one correct matchings. So observe carefully and match them. See, elliptical orbits. They have given some concepts and their discoverers, proposers. They have given here. See, elliptical orbits concept was proposed by Sommerfeld. Sommerfeld proposed it. So elliptical orbits. Next one, stationary orbits. The concept of stationary orbits was proposed by Niels Bohr. Bohr proposed stationary orbits. What about uncertainty principle? Uncertainty principle was proposed by Heisenberg. Heisenberg proposed uncertainty principle. What is the last one? Dual nature of electron. Dual nature of electron was proposed by de Broglie. So elliptical orbits Sommerfeld, stationary orbits Niels Bohr, uncertainty principle Heisenberg, dual nature of electron de Broglie. Now what will be the correct matching? This is elliptical orbits Sommerfeld, stationary orbits Bohr, uncertainty principle Heisenberg, dual nature de Broglie. This is the correct matching. Observe once. Okay, next let us go to next question. Analytical approach type questions. First among them, the work function of some metal is listed below. So work functions are given for certain metals. The number of metals which will show photoelectric effect when light of 300 nanometers wavelength falls on the metal. See here, the work functions. What is meant by work function here, which is also called threshold energy, which means the minimum amount of energy required by that metal to eject electrons from their surface is called work function or threshold energy, that is given for different metals shown here. Now certain for light of certain energy with wavelength 300 nanometers made to fall on these all metals. Now which of these metals can show photoelectric effect, they're asking. To know that, first we have to identify the energy associated with this photon, which is having 300 nanometers wavelength. Now, if the energy passed is greater than the work function of this metal, then that metal can exhibit photoelectric effect. If the energy passed onto the metal surface, if it is less than of that of its work function, then that metal cannot release electrons and it cannot exhibit photoelectric effect. So first we have to calculate the energy of the light passed onto these metal surfaces. Let us see the solution. The energy of the radiation must be equal to or greater than the work functions of the metals to show photoelectric effect. So we need to convert the wavelength into energy. So see, energy of the radiation is equal to hc by lambda. We have a relation for the energy with the wavelength as E is equal to hc by lambda, where E is representing energy, h is Planck's constant, c is velocity of radiation, and lambda is the wavelength. So if we substitute these all values, we get it as, so we have these all values because h and c are constant, their values are known, and here it should be into 3 into 10 to the power of 8 meters per second. Now if you calculate this, we get it as 6.626 into 10 to the power of minus 19 joules. This is energy of the radiation. But here work functions are mentioned in electron volts. So let us convert this energy of the photon also into electron volts. 1 joule is equal to 6.24 into 10 to the power of minus 18 electron volts. So if we convert this total energy in joules into electron volts, we get it as this 4.134 electron volts. So the energy of the photon passed on to the metal surfaces is 4.134 electron volts. Now the metals which are having their work function either equal to this energy and less than this. Those metals only can exhibit photoelectric effect. See, which are having their work function equal or less than this 4.134 can show. So lithium can show, sodium also can, potassium also, and even magnesium. Under these three metals, if you observe, for these all, their work function is greater than the energy of that light radiation made to fall on them. So these metals, they cannot show photoelectric effect. Only these four metals can show photoelectric effect. Okay, only four. So the correct answer will be now A. Next question. Consider the ground state of chromium or the ground state electronic configuration of chromium. The number of electrons with azimuthal quantum number L equal to 1 and 2 are respectively. So from the ground state electronic configuration of chromium, they are asking to calculate the number of electrons which azimuthal quantum number value 1 and with L is equal to 2. For that, let us see the electronic configuration or ground state electronic configuration of chromium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. This is the configuration. Now, L is equal to 1, that represents P subshell. L is equal to 2 represents D subshell. So we have to find out the number of electrons present in the P subshell and the number of electrons present in the D subshell for the chromium respectively. See first with L is equal to 1, that means electrons in the P subshell. Totally how many electrons are there? Here 6, 6. How many? Totally 12 electrons are there. Now let us calculate the number of electrons present in the D subshells. That is L is equal to 2. How many are there? Only 5 electrons are there. So 12 and 5 is the correct answer. There are 12 electrons in the P subshell. That means with azimuthal quantum number L value 1, and there are 5 electrons with the azimuthal quantum number value 2. 12 and 5. Where is it? The B option. Okay. Next one. The de Broglie wavelength of a tennis ball of mass 60 grams moving with a velocity of 10 meters per second is approximately. We are asking to calculate de Broglie's wavelength. So according to de Broglie, to calculate the wavelength of a particle, we have equation as lambda is equal to h by mv, where lambda represents wavelength, h is Planck's constant, m is the mass of that body, and v is velocity of the body. So now let us substitute these all values. H value we know as it is Planck's constant 6.625 into 10 to the power of minus 34 joule second, and mass of the body or tennis ball is given 60 grams. So let us convert this into SI units into kgs. 60 into 10 to the power of minus 3, and the velocity is given in meters directly. So let us substitute these all values. We get it as 1.1 into 10 to the power of minus 33 meters. So in the given options, the approximate one is 10 to the power of minus 33 meters. 1 into 10 to the power of 33, nothing but 1. So we get it as 10 into 10 to the power minus 33 meters. Where is it? The first option. Okay, next. Consider the ground state configuration of chromium. The number of electrons with azimuthal quantum L into 2. Oh, we have seen all this already. We get it as 12 and 5. Okay, next question. The probability density plots of 1s and 2s orbitals are given in the figures. See, for these two, probability orbital diagrams are shown, 1s and 2s orbitals. The density of dots in a region represents the probability of density of finding the electrons in the region. On the basis of above diagram, which of the following statements are correct? Let us see the statements once so that we can understand. 1s and 2s orbitals are spherical in shape. Of course, both are spherical. The probability of finding the electron is maximum near the nucleus. No. The probability of finding the electron near the nucleus is 0. It is not maximum. We cannot find any electron near the nucleus. There are no electrons near the nucleus. So the probability of finding the electron near the nucleus is 0. Okay. It is incorrect statement. It is not correct. Probability of finding the electron at a given distance is equal in all directions. Yes, for the s subshells, s orbitals, the distance from the probability of finding the electron at a given distance is equal in all directions. As these s orbitals are spherical in shape, the distance is equal in all directions. Okay, the probability of finding the electron near the nucleus is 0, not maximum. So only the second statement is incorrect. Next, statement type questions. The first question, first statement, energy levels are also called stationary orbits. Yes, in the Bose theory we have seen the energy levels are also called as stationary orbits. That's the correct statement. Next one, energy of an electron remains constant as long as it revolves in the given orbit. Yes, as long as an electron revolving the same orbit, it neither gain energy nor lose energy. Its energy will be constant. So second statement is also true. If both statements are true, what will be the correct option? Principal quantum number determines the energy and size of the orbits, but not orientation. No, this is A. Both the statements are correct here. Okay, A is correct answer for this. Next question. Bohr's orbits are called stationary orbits. Yes, just now we have seen this. Bohr's orbits are also called stationary orbits because as long as electrons are revolving in the same orbit, they neither gain energy nor lose energy. They will be the same constant energy. That's why these orbits are also called stationary orbits. This is correct. Next statement. The angular momentum of the electron revolving in a stationary orbit is equal to integral multiples of h by 2 pi. Yes, the angular momentum mvr is equal to nh by 2 pi, where that is integral multiples of h by 2 pi. So this is also correct statement. Both are correct statement. Then what will be the correct answer? A. Next question. Statement 1. The principal quantum number determines the orientation and energy of the orbital. Principal quantum number determines the orientation and energy of the orbital. Is it correct? No. Principal quantum number determines the size and energy. Energy is correct only, but not the orientation. Principal quantum number determines the size and energy of the orbit, but not orientation. So this is a not correct statement. Next statement, angular quantum number determines the three-dimensional shape of the orbital. Yes, angular quantum number, which is also called as azimuthal quantum number, that determines the shape of the subshell or orbital. This is the correct statement. Now, statement 1 is wrong, statement 2 is correct. Where is it? The fourth one. Statement 1 is correct, incorrect. Statement 2 is correct. D is correct option for this. Okay. Next question. Two electrons of an atom may have identical values of N and L, N, L and M values. Isn't it? Yes. Two electrons in an atom may have three quantum number values same. That may be N, L and M. If the electrons two are present in the same orbital, then those two electrons present in the same orbital will get the first three quantum number values the same. That means principal quantum number, azimuthal quantum number, and magnetic quantum number values will be same for those three electrons which are in the same orbital. But only spin quantum number value will be vary for those. So this is a correct statement. Second one, two electrons of equal energy occupying p orbitals of an atom may have parallel spin. Of course, two electrons with the equal energy may have parallel spin. Yes, according to Hund first the electrons in the same energy or in the degenerate orbitals will occupy with the single electrons first. So the electrons in the same energy may have parallel spin. It is also correct statement. So both 1 and 2 are correct statements. So the correct answer is A. Next, assertion reason type questions. See the first one. For n is equal to 3, L is equal to 0, and 1, 2, and 1 and 2, and M is equal to minus 2. Okay, they're asking for principal quantum number value n is equal to 3. L values are 0 to 2, and M values are from minus L to plus L plus 2. Isn't it? Yes, it is correct. Here, for n is equal to 3, L values will be from minus L to 0 to n minus 1. So n value is given as a 3 here. So L values will be from 0, 1 and 2. So this is correct. And M values may be from minus 2 to plus 2 including 0. Because if L is equal to 0, M value will be 0. If L is equal to 1, M values will be from minus 1 to plus 1. If L is equal to 2, minus 2 to plus 2. So this is also correct. Assertion is correct. Now, reason let us see once. For a given value of n, the values of L are all integers from 0 to n minus 1. Actually, it is the correct reason why these values are given. So, L values are from 0 to n minus 1. That is correct. And for a given value of L, M values are from minus L to plus L including 0. This is the correct reason for it. So assertion, reason both are correct, and reason is the correct explanation why those values are given. So where is it correct answer now? A. Okay. Next question. The main shell with principal quantum number n is equal to 2 has 4 orbitals present in it. Isn't it? Is it correct? Let us see this reason also. The number of orbitals present in a shell is given by n square. So if it is n square, if you take say n is equal to 4. N is equal to 4 means second shell. Second shell contains two subshells, S and P. 2S and 2P we call them. Isn't it? In the 2S subshell, only one orbital. What about 2P subshell? 2P subshell contains three orbitals. What are they called? 2Px, 2Py, 2Pz. Totally three orbitals are there. Now, total number of orbitals in the second shell, 1 plus 3, totally 4. So there are 4 orbitals, it is correct, and the formula given is n square. It is also correct. Both are correct here. So the option is A. Okay. Thank you for watching our video. Please subscribe our YouTube channel AIMS Today for latest updates and recorded videos.